Welcome to this new arXiv paper pitch. It is about Padmanabhan's boundary variational principle for electrodynamics and Young-Mills theory. My name is Benjamin Koch, and first of all, many thanks to Hamza Padmanabhan for consenting to coin the name after her father, Paddy. Further thanks to many colleagues who helped me with the preparation of the manuscript. So let's get started. In 2006, Tanu Padmanabhan wrote a paper which was about a novel variational principle, which he suggested there, and he applied it for gravitational physics, in particular general relativity. And here's the paper. It is called "Why Does Gravity Ignore Vacuum Energy?" And it is not unnoted. It was also published in International Journal of Modern Physics D. Has 42 citations, but given Padmanabhan standards, it's slightly under the radar. Here's the abstract. And one realizes that this paper is about the cosmological constant problem. Already in the abstract, he notes that while the matter energy momentum tensor, in particular the equations of motion, are invariant under a shift of this tensor, gravity is not invariant under this shift. It's very sensible. And this is actually the core of the cosmological constant problem. Then he proceeds to propose different equations which contain null vectors, which kind of do not have this problem, or do have this problem in very weaker or different way, because he then shows that the cosmological constant, whose value is surprisingly small, appears as a constant of integration of his equations. And this is the key thing here. And then he shows that these modified equations can be obtained from a modified variational principle, which we will call the Padmanabhan variational principle, delta P. So what is this modified variational principle? It has, in the essence, has 4 steps. First, one defines an action, which is a boundary action. Then one has to define a variation, which looks like a gauge transformation, but is not. Then one has to impose that these variations vanish on the surface. And finally, one has to define these surfaces as a class of boundaries. This is quite subtle, this definition. And I copied just the part of the paper where this is mentioned. So one has to choose a Rindle horizon and killing vectors and so on. And here is what artificial intelligence would interpret these surfaces as. Well, now as the content of my paper, the hypothesis is that this variational principle is not just a peculiarity of gravity, but should also work for other much simpler gauge theories as well. And the content of the paper is that I take these steps A to D and apply them in slightly modified form for electromagnetism and Young-Mills theory. And the outcome will then be field equations, which are very similar, if not identical to these theories we thought of. But one obtains integration constants which allow for CP violations and gauge boson masses. And these are explicit breakings, or not explicit, these are breakings of symmetries. And since they come in the process of integrating, one could call them spontaneously broken symmetries. So this is like the punchline. First of all, the take-home message is that one can apply this variational principle of Padmanabhan also for the much simpler theories of electromagnetism and Young-Mills theories. And the second point is that from this perspective of this Padmanabhan principle, the 3 problems which are known as the cosmological constant problem, which comes with the value of lambda, that's the paper of Padmanabhan, but also the strong CP problem, which comes with a coupling called theta, and also the Higgs hierarchy problem, which comes with the value of the gauge boson mass, m. These look like brothers and sisters, or at least cousins, because they appear in the same way in this procedure. More details you can see in the paper, and thank you very much.